All right, guys, so we've been having discussions, some fruitful discussions on power. Now, there's one other concept that needs to really be introduced in the context of power, and it's the idea of complex power. Complex power itself leads to some very interesting and fruitful results, and it gives you a better overall understanding as to certain design requirements for things like transmission lines and things like that. Because transmission lines and other such power delivery systems must be designed in such a way that they're not just accommodating what they call the real power that's being delivered to a load, but they must accommodate for more than that in general. So let's begin our discussion on this new parameter called complex power. Now, the complex power, and let me start with the definition. We use the letter S to denote it, capital S, and by definition, it is the real power plus J times the reactive power. So by its very nature, it happens to be a complex number, right? Now, the units of complex power are a little bit different than that of real power, which was in watts. So just remember that real power is in watts. Remember that the reactive power even though it should be a volt times amp, it's misleading to actually call that a volt times amp. This was in VARs. Similarly, the units of complex power is in a volt times amp. And again, the reason we actually have this distinction between all three of these powers, even though really technically they should have all the units, is the same units, is that they play in the circuit are going to be very, very different, right? So that's one of the reasons why we make this distinction. Now, one thing that should be relatively easy to show is that if you actually take this complex power, right, one of the things that you can do is you can actually construct a right angle, a right triangle with respect to this. So suppose that we construct a right triangle. The inner angle that I'm denoting here is theta. And on one side of the triangle, we actually have the reactive power, while over here, we actually have the average or real power. One of the things that, based on this triangle, we can write down mathematically is that the tangent of this angle is, well, it's the opposite over the adjacent side. That's Q over P. And we should be able to identify this arbitrary angle, at least initially, as the power factor angle. And to show this, consider the following. Remember, the way we can calculate the real power is magnitude of the voltage, magnitude of the current divided by 2 times the cosine of the power factor angle like this. If you calculate the reactive power, it is the magnitude of the voltage, magnitude of the current divided by 2 times the sine of the power factor angle like this. And if you actually construct, well, Q over P, well, this is Vm Im over 2 times the sine of the power factor angle divided by Vm Vi over 2 times the cosine.